When we talk about a software delivery pipeline, we are referring to the full chain of automated steps that transform source code written by developers into a running application available to end users. In a traditional DevOps approach, this chain is designed primarily for speed and reliability. Write code, test it, build it, and deploy it as fast as possible. DevSecOps extends this philosophy by embedding security at every single step of that chain, rather than treating it as an afterthought checked only at the end. This course explains precisely what that means in practice, which security actions are performed at each stage, why they matter, and what concrete threats they address. By the end of this course, you will have a clear mental map of security responsibilities distributed across the entire pipeline. Why security cannot wait until the end. For decades, security was treated as a gate at the end of the development process. A team of security experts would receive a nearly finished application, run some tests, find vulnerabilities, and send the application back to developers for fixes. This approach had a critical flaw. The later a vulnerability is discovered, the more expensive and time-consuming it is to fix. Imagine a developer writes a piece of code that contains a SQL injection vulnerability. If this is caught the moment the code is written, the fix takes minutes. If it is caught 6 months later, after the code has been integrated into dozens of other modules, tested, and deployed to a staging environment, the fix can take days and may require rethinking entire parts of the application. This is the core argument for shifting security left, moving security checks as early as possible in the pipeline. In DevSecOps, every team member shares responsibility for security. Developers, testers, operations, engineers, and security specialists all contribute to building a secure product. The pipeline itself becomes a security enforcement mechanism. Stage 1. Code writing, the developer's workstation. Security begins before any automated pipeline even runs. When a developer writes code locally on their workstation, several practices and tools should already be active. First, developers should follow secure coding guidelines. These are documented rules that prevent common mistakes. For example, always validating user input before processing it, never hard-coding passwords or API keys directly into source code, and using prepared statements instead of raw string concatenation when building database queries. Second, integrated development environment plugins can flag security issues in real time as the developer types. For example, a plugin might immediately warn a developer who writes a function that stores a password in plain text instead of hashing it. Third, secrets detection tools are essential at this stage. A developer might accidentally include a private key or a database password in their code. Tools designed to scan for secrets can catch this before the code ever leaves the developer's machine. A classic real-world example. A developer at a company accidentally commits their cloud provider access key to a public code repository. Within minutes, automated bots scanning public repositories find the key and use it to spin up hundreds of virtual machines for cryptocurrency mining, costing the company thousands of dollars. Catching this at the workstation stage prevents the incident entirely. Stage 2. Version control and code review. Once a developer pushes their code to a shared version control system, such as Git, the next security layer activates. Peer code review is one of the most powerful and underused security tools available. When a second developer reads through the new code before it is merged into the main branch, they may spot logical flaws, missing access controls, or improper error handling that the original author overlooked. For example, a reviewer might notice that a new API endpoint returns sensitive user data without first checking whether the requesting user has permission to see it, a broken access control vulnerability. Automated static application security testing tools are typically triggered at this stage. Static application security testing analyzes the source code without executing it, looking for known patterns associated with vulnerabilities. It can detect issues such as cross-site scripting risks, insecure use of cryptographic functions, or SQL injection patterns. The analysis runs automatically when a developer submits a pull request, and the results are visible directly in the code review interface. If critical issues are found, the pipeline can be configured to block the merge until they are resolved. Software composition analysis tools also run at this stage. Modern applications rely heavily on third-party libraries and open-source components. Software composition analysis scans the list of dependencies used by the application and checks them against databases of known vulnerabilities. For example, if an application uses an old version of a popular logging library that has a known critical vulnerability allowing remote code execution, the software composition analysis tool will flag it immediately, allowing the team to update the dependency before the vulnerable code ever reaches production. Stage 3. Build and compilation. Once code passes review and is merged, the pipeline typically compiles or packages the application. This is where the binaries, container images, or deployable artifacts are created. At this stage, the integrity of the build environment itself must be verified. If an attacker manages to compromise the build server, they could inject malicious code into every application built on that server, even if the source code is perfectly clean. This type of attack is called a supply chain attack. A well-known real-world example is the SolarWinds incident, where attackers compromised a build system and inserted malicious code into software updates that were then distributed to thousands of organizations worldwide. To protect against this, build environments should be isolated, ephemeral, created fresh for each build and destroyed afterward, and access to them should be strictly controlled. Build logs should be stored and auditable. When the application is packaged as a container image, which is very common in modern pipelines, the base image used should be scanned for known vulnerabilities. For example, if the base image is built on an outdated operating system version with unpatched security flaws, any application deployed from that image inherits those flaws. Container image scanning tools check the layers of an image and report vulnerabilities found in the packages installed within it. Stage 4. Automated testing in a staging environment. Before reaching production, the application is deployed to a staging environment that closely mirrors the real production setup. This is where dynamic security testing takes place. Dynamic application security testing tools interact with the running application, simulating the behavior of an attacker. Unlike static application security testing which reads code, dynamic application security testing sends real requests to real endpoints and observes how the application responds. It can discover vulnerabilities that only appear when the application is actually running, such as authentication bypass issues, session management flaws, or server misconfigurations. For example, a dynamic application security testing tool might discover that the application's password reset feature does not properly expire reset tokens, meaning an attacker who intercepts an old reset link could still use it hours later. This is a vulnerability that would be very difficult to detect by reading code alone. Penetration testing, conducted by human security experts, can also be scheduled at this stage, especially before major releases. Human testers bring creativity and contextual understanding that automated tools lack. They can chain multiple small weaknesses together to demonstrate a realistic attack path that no single automated tool would flag on its own. Fuzz testing is another technique applied here. It consists of sending large volumes of unexpected, malformed, or random input to the application to see if it crashes or behaves in unexpected ways. Crashes can indicate memory management vulnerabilities that might be exploitable. Stage 5. Deployment to production. When all previous security checks have passed, the application is deployed to the production environment. Security does not stop here. The deployment process itself must follow the principle of least privilege. This means that the automated system performing the deployment should only have the exact permissions needed to do its job, nothing more. For example, a deployment script that only needs to update a web application should not have the permissions to modify database schemas or access unrelated services. Infrastructure configuration should be validated against security baselines before deployment. For example, verifying that no unnecessary ports are open, that encryption is enabled for data in transit, and that default credentials have been changed on all services. Immutable infrastructure is a practice that further reduces risk. Instead of modifying a running server, a new server is created from a known good configuration and the old one is replaced. This eliminates entire categories of risk associated with configuration drift, where a server gradually accumulates undocumented changes over time that may introduce vulnerabilities. Stage 6. Monitoring and incident response in production. Once the application is live, continuous monitoring is essential. Even a perfectly secured pipeline cannot guarantee zero vulnerabilities in production. New vulnerabilities are discovered in dependencies, attackers find novel exploitation techniques, and misconfigurations can creep in through operational changes. Runtime security monitoring tools watch the behavior of the application and its infrastructure for anomalies. For example, if a web server that normally only makes outbound connections to a database suddenly starts making connections to an unknown external IP address, this is a strong indicator of compromise. Security information and event management systems collect and correlate logs from across the entire infrastructure, enabling security teams to detect attack patterns that span multiple components. For example, a series of failed login attempts across many user accounts, followed by a successful login from an unusual geographic location, might indicate a credential stuffing attack. Vulnerability scanning of production systems should also be performed regularly. Even if a system was deployed securely, new vulnerabilities in its components may be published days or weeks later. Continuous scanning ensures these are detected and patched promptly. Finally, a clear incident response plan must be in place. This defines who is responsible for what when a security incident is detected, what steps to take to contain and investigate the incident, how to communicate with affected users, and how to prevent recurrence. The security pipeline as a whole. Key principles. Looking at all these stages together, several key principles emerge that define the DevSecOps approach to pipeline security. Security is continuous, not a one-time check. It runs automatically at every stage, every time code changes. Security is shared. Developers, operations teams, and security specialists all contribute. No single team owns security exclusively. Failures block progression. If a critical vulnerability is found at any stage, the pipeline stops and the issue must be resolved before the code can advance further. Everything is auditable. All security checks, their results, and the decisions made about them are logged and traceable. This is essential for compliance with regulations and for post-incident investigation. Defense in depth applies to the pipeline itself. Multiple overlapping security controls mean that if one check fails to catch a vulnerability, another further down the chain may catch it. A practical summary of which tools correspond to which stages. Code writing stage. Secure coding practices, integrated development environment security plugins, secrets detection. Code review stage. Static application security testing, software composition analysis, peer review. Build stage. Build environment hardening, container image scanning, supply chain integrity verification. Testing stage. Dynamic application security testing, penetration testing, fuzz testing. Deployment stage. Least privilege enforcement, configuration validation, immutable infrastructure. Production stage. Runtime monitoring, security information and event management, continuous vulnerability scanning, incident response. Understanding this full picture is what distinguishes a DevSecOps practitioner from someone who simply knows a collection of security tools. The tools only have value when they are placed at the right stage, configured to block on critical findings, and connected to a team that knows how to act on the results.